deliver this talk. First of all, can you hear me? Can you see my presentation, including the cursor? Okay.
Yes, yes, we do.
Good. Thanks. So I'm going to talk about the application of fluorescence spectroscopy in probing distribution of counterions around polyelectrolytes, and this was a topic to which we use both experiments and computer simulation, because I think that it's well, not unique, but quite rare that in our group we do both simulation and various experimental techniques. But still, we needed a collaboration with this other group, mainly in the field of synthesis. And in that matter, we collaborated with Institute of Macromolecular Chemistry of the Czech Academy of Sciences, and also with the Institute of Theoretical and Physical Chemistry of the National Research Foundation in Athens, in Greece. This is the group of Stelios Pispas, who is also in the audience of this conference. So actually, the topic we focused was dealt many years ago, and it was dealt in the field of colloid chemistry first. It was already in 1940 that Hartley and Rowe pointed out that acido-basic indicators could be used for detecting the different local concentration of H+ ions close to charge interfaces of colloids. So it was the first time that this idea was published. And actually, really, many years later, in 1977, there was a paper in Journal of Physical Chemistry by Fernandez and Fromherz, who tried to use this using either aminocoumarine or hydroxycoumarine as an acido-basic indicator, and then they use it for surfactant micelles, either for sodium rudolph sulfide or for cetyl trimethyl ammonium bromide, and they really found out that these acido-basic fluorescent indicators exhibited significant shift of their titration curves when adsorbed to the surface of those polymeric micelles according to charge of those micelles. So for instance, let's imagine that we have an indicator which is weak acid, and we have a negatively charged interface. So in that case, we will have a higher local concentration of protons around this interface, and we will experience titration curve which is shifted to the right. Or there is another approach to that issue. We can also consider that due to the potential at the interface, the protons need excess free energy to be released to the bulk solution, and that is why the acido-basic indicator itself behaves like a weaker acid, and that's the reason why it has this titration curve shifted to the right. So actually, we tried to do the same already 20 years ago. We tried to do the same with polymeric micelles, and we use polymeric micelles of polystyrene polymethacrylic acid, and we use such kind of indicator. It's the decanyl aminofluorescine, which very firmly binds at the interface of those micelles. And then we followed the fluorescence measurement. We measure the fluorescence as a function of pH, and this is how it looks like for the free probe. So this is the decanyl aminofluorescent, which in water, it has pretty much the same titration curve as normal fluorescence. So this, the inflection point is corresponding to the pK of fluorescein, the anion, and which this is around 6.4 or something like that. If we did the same with micelles, we really found that the titration curve was shifted towards higher pK. So indeed, due to the negatively charged polymethacrylic acid corona, this fluorescent dye behaved like a weaker acid. But you can see here that the situation is not that simple, that the curve is not only shifted, but also the slope is different. And it's due to the fact that not only the pK is changing during the titration, but also the degree of ionization of the polymethacrylic acid. So the situation in this case is more complex, and moreover, the dielectric permittivity inside the micelles is different than the dielectric permittivity in bulk solution. So this is the another thing that influences the acid-basic equilibria in this case. So to compare this micelles or micelles with this acid-basic indicator experiencing the same kind of environment, we did the same experiment with polystyrene block polyethylene oxide, and it indeed was shifted even without the presence of charged corona. It was shifted towards the higher pH, which indicates that it behaves like a weaker acid. And only from that we were able to obtain the interfacial potential by comparing the apparent pK shifted due to the charge interface and intrinsic pK, which is just due to the different dielectric permittivity on the surface. And the interfacial potential was around 50 millivolts, which was quite comparable with those found by Zito potential measurement. So in a more general way, how can we follow counterion concentration by fluorescence spectroscopy? There are two ways to do so. One is collisional quenching of fluorescence by heavy ions. So if we use the heavy ions, we can measure how the fluorescence of the probe is quenched by them, and from that we can conclude what the local quenching concentration is, or by fluorescence pH indicators, which is in fact the static quenching, because when, for instance, the indicator like fluorescein is protonated, it no longer fluoresces, so you can say then that proton acts as a static quencher of this probe, and from that you can obtain the local pH, either local pH or effective pK of that probe. So to treat this situation in a more quantitative way, we can divide the contribution to the chemical potential as those which are related to concentration, and those which are related to non-ideal contribution by the mutual interactions of the particles. And after that, we can obtain the expressions for expressing local pH and effective pK using this shift delta, which is related to those non-ideal contributions to chemical potential. So we can use various fluorescent indicators. So this is the one which was used in our very first study 20 years ago. Fluorescein has two ionizable groups. In order to emit fluorescent, both of them must be ionized. So this transition is crucial for fluorescence. PK for that transition from monoanionic to dianionic form occurs at pK 6.4. Another possibility is umbelliferon, which is the pK shifted to a little bit higher value, about 6.8. And that is why we really focused on umbelliferon, because we still wanted to use polymethylic acid for further studies. But in this case, the transition occurs in the region where polymethylic acid is still fully ionized. So the behavior is not complicated by changing degree of ionization of polymethylic acid during the titration experiment. And we decided to perform this experiment to make the things more simple, to make it just with a single polymer chain. So we need to first to label polymethylic acid with umbelliferon, which was not that easy, but our colleagues from the Institute of Macromolecular Chemistry in Prague were able to find a solution. So they synthesized these derivative of umbelliferon, which served as fluorescent ATRP initiator, and then they just performed the ATRP polymerization and prepare polymethylic acid, which was labeled at the end with this umbelliferon. So this is the characterization of this polymethylic acid by both dynamic light scattering and small angular X-ray scattering. So it really, it's even at relatively high ionic strength, it's in a very stretched conformation. When the pH is around 8 or 9, you can fit it very easily with the form factor for cylinder. And this is how the zeta potential and the hydrodynamic radius depends on pH. So you can see that in this area, which is interesting for us because it's the range at which the fluorescent indicator undergoes the transition from fluorescent form, from anionic form to the protonated form, which is non-fluorescent. In this area, really, the zeta potential is here. The zeta potential is here, so it's negatively charged, and it's in expanded conformation. And the same happens with fluorescence anisotropy. So from these measurements, you can see that the probe is freely rotating, and it's not influenced by any conformational behavior of the chain. So when we measure the excitation and emission spectra, we can see here that the emission is increasing with increasing pH, and if we now plot the normalized fluorescence intensity as a function of pH for various ionic strength, we can not only see the shifts for various the shifts in the pK value of the fluorophore, if it is the umbelliferon which is attached to the polymer chain, but also we can see that this shift is decreasing with increasing ionic strength because of the screening of the effect of the protons around the polymer chain by other counterions, in this case by sodium counterions. And this is how it looks like when we put this plot this effective pK as a function of salt concentration. So here you can really see that the pK, effective pK, is decreasing with increasing salt concentration. So now, as regards the comparison of the measurement with this simulation, what is unique in simulation is the fact that in simulation, we can independently look both at the concentration of counterions in the vicinity of probe, and we can also look at the degree of ionization of the probe itself. So in the simulation that we performed, the ionization of the label is implemented as a Monte Carlo move, so we can follow if the label is ionized or if it's protonated, and then we can just simulate the titration curve, because we can just plot the average degree of ionization as a function of pH. And if we do that, in the same way as in experiment, we obtain the shifts in the titration curve caused by the screening of electrostatic interaction due to the increasing ionic strength. And more than that, we can compare the two outputs from the simulation. This green curve is an experimental value, and this red curve is a simulated titration curve. And we can compare it with the values of the shift, which are calculated from the distribution function of counterions. This radially average distribution function, which is calculated from the simulation as well. And using this formula, we can calculate the PK shift, and you can see that the trend is similar, but there are some differences, and these differences are caused mostly by the fact that this is radially averaged distribution function, but the probe itself experience the neighborhood which does not have this symmetry, because it's located at the end of the polymer chain. So from the simulation, what affects most the results is not the polymer concentration. You can see that curves does not change with polymer concentration very much. The degree of ionization is also not affecting the results that much. But what really does affect the results, you can see the significant shifts in the titration curves, is the distance of this OH group from the rest of the polymer chain. So this is without the spacer. This is the spacer which is the length of one unit, and this is the length of the spacer which is the length of two monomeric unit of the polymer, and with the increasing distance of this OH group from the rest of the chain. Of course, the effect of the counterion distribution around the chain is gradually disappearing. So now back to the application of dynamic quenching as a tool for studying counterion distribution. What we did in this study was, again, we again used this polymer, this umbelliferron labeled polymetaphilic acid, and we try to use this oppositely charged polyelectrolyte, this the double hydrophilic polyelectrolyte, this group, which acts as a dynamic quencher of the fluorescence. And what happens if we mix this polyelectrolyte with this double hydrophilic polyelectrolyte is the formation of core shell nanoparticles, in which, of course, the probe experiences dynamic quenching by these chains. So this is how it behaves when we mix the two polymers. We have some peak which corresponds to the formation of particles. This is the dynamic light scattering. This is the RH as a function of the ratio, the charge ratio between the two polymers, and you can indeed see that it forms spherical particles in this area, which this is the TM image of those particles. And now, if we come to measurement of fluorescence, and this time, because it's the dynamic quenching, we measure the fluorescence emission decays, and we found out that we can use a micellar quenching model for following the decay, and from that we are able to see the transition from this type of structure to this type of structure in which the quenching is much more pronounced. But what is important is that it still remains a dynamic quenching. So it shows us that the core of the particle is mobile, and the behavior of these macromolecular quenchers is very similar to that which we would expect for low molar mass quenchers in micelles, which is quite interesting. So that's how it behaves in dynamic quenching. So I came to the conclusions. I showed us that we can use fluorescence measurements to probe the concentration of counterions and the correspondingly the potential around the interface by measuring both quenching and the PK shift of fluorescent PK indicators. I showed you that the fluorescence measurements for PK shift are in semi-quantitative agreement with molecular dynamics and combined with Monte Carlo simulations, and these simulations show the influence of ion correlation effect on acido-basic behavior of the fluorescent probe. And also, last but not least, what is interesting is that if you have a interpolyelectrolyte complex in which one of the poly ions acts as a quencher, it behaves in the same way as low molar mass quenchers. So in this interpolyelectrolyte nanoparticles, we still experience dynamic quenching, and this emission decay can be described using the micellar quenching model. So I would like to acknowledge the support from European Union, to acknowledge the beam time at ESRF in Grenoble, and I thank you all for your kind attention.
Thank you.